In this lesson, we're going to take a look at electromagnetic radiation, electromagnetic waves. Now, these are like mechanical waves in the sense that they are disturbances that are transferring energy, but they're unlike mechanical waves in that they're not transferring energy by the vibration of particles. Rather, these transfer energy through the vibration of what we call fields. Now, a vibrating field, or a field, I guess, is just a region of space that can exert a force on something else, so an energized region of space. If you've ever taken two magnets and brought them close to each other, you know that one magnet will either attract or repel another magnet, and they'll jump together or push apart without touching. And that's because the magnets are creating a field that the other magnet interacts with. Electric charges can do the same thing. That's why you can have static cling, or things that repel each other. They can do that due to static charge as well. Now, an electromagnetic wave consists of two fields vibrating at right angles. And we represent these with these lines here. These red lines represent electric fields, and you can see this electric field is vibrating down, and then it's vibrating back up. Whereas the magnetic field, the blue one, is vibrating out of the page and then back into the page. And so these are vibrating at right angles, but you'll notice it's a transverse wave because the vibration is out of the page, into the page, up and down, but the motion is to the right. And the distance between crests is the wavelength. That's what that's showing us. So thanks Wikipedia for giving me this cool little animation. This is what an electromagnetic wave will look like if we could represent its changing fields in time. And it turns out that these things can move through a vacuum because the electric field and magnetic fields actually create each other. When we have a changing electric field, it induces a changing magnetic field. And when we have a changing magnetic field, it induces a changing magnetic field. Electric, whatever I didn't say. So because we have a changing electric field, we get a changing magnetic field, which in turn produces another changing electric field. And so these can propagate through a vacuum. They can travel through matter. Just because they can travel through space doesn't mean they can't travel through matter. But when they are traveling through space, they are traveling very, very rapidly. When they move through a vacuum, they're going at 300 million meters per second. That's 3 times 10 to the 8th meters per second. In miles per second, that's 186,000 miles per second. So light's moving really, 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 really fast. Now, it does slow down a little if it's moving through matter, and different matter is going to slow it down different amounts. But for us, we're just going to assume that the light is traveling at 300 million meters per second. Now, I said light, but light is not the only electromagnetic wave. There's a whole range of these different wavelengths that we call the spectrum. We do divide it up by wavelength or frequency. Remember, as wavelength increases, frequency decreases. So here you can see we have the very longest waves, which are radio waves, and as they get shorter and shorter and shorter, we move through microwave, infrared, visible, ultraviolet, X-rays, and finally gamma rays. Down here, this shows us our frequency. The frequency is starting small. I say small, but that's 10 to the 6th hertz, and goes up to a very much higher frequency, 10 to the 21st hertz. So because electromagnetic waves travel so fast, their frequencies are also very, 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 very high. And what we get when we start breaking this down is we see that we use different waves for different things. We'll break them up into wavelength and also frequency. Remember, as wavelength increases, frequency decreases. But the cool thing about electromagnetic waves, or one of the cool things, is that the frequency is related to the energy. Higher frequency waves have higher energy, which means these gamma rays over here carry more energy than these radio waves down here because they have a higher frequency. Now, amplitude does matter. Amplitude can affect the power of the wave. Frequency can affect the energy of the wave. So we can change the amplitude. Radio signals from radio stations, if they want to cover a greater broadcast area, they're going to increase the amplitude of their wave, which they got to have a license to do. Okay. These waves, the radio waves, microwaves, that spectrum of the electromagnetic spectrum is very highly regulated because we use it for so much. We use it to transmit lots and lots of data. In fact, that's primarily what we do with radio waves. They're the longest electromagnetic waves. They carry the least amount of energy. They're anything from 1 millimeter in wavelength to longer, and the 1 millimeter to 1 meter is actually called the microwave spectrum. It's the top end of the radio waves. So they're long waves with a low frequency, and we use them to carry information wirelessly. Everything from TV and radio to cell phones and Wi-Fi uses radio waves to communicate. Radar for navigation. Okay, microwaves fall at the top end of this. Like I said, when I say microwave, I don't want you to think microwave oven. Although microwave ovens do use microwaves, I want you to think short radio waves. Microwave ovens use a certain wave, about 12 centimeters long, to actually vibrate water molecules, and that vibration of the water molecules heats the food, and then convection and conduction will allow all of the food to get hot. So, like I said, they use about 12 centimeter long waves in order to do that. Next up on the spectrum is infrared. So this is after microwaves, but before red. In fact, that's what infra means. So these are 1 millimeter to 750 nanometers long. A nanometer is about a billionth of a meter. So if you take your meter stick and cut it into 1,000 pieces, that's a millimeter. If you take each one of those and cut it into 1,000 pieces, then you'll have a millionth of a meter. And if you take one of those and cut it into 1,000 more pieces, then you're dealing with a nanometer. So this is a very, 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 very short wave, and 750 nanometers is about where we can start to see things, where we start to see the color red. So this is actually literally before red. Infrared radiation is actually pretty useful to us. We use it for communication. We also use it for imaging because it carries thermal energy. So if we're trying to see heat, what we do is we build a camera that can detect this infrared radiation, and then a computer to give it a false color so we can see what's going on. Most of the sun's energy reaches Earth as infrared radiation, and in fact the atmosphere does a very good job of trapping that here to keep Earth nice and warm and a comfortable place to live. CO2 does an extra good job of that, and so when we put CO2 in the atmosphere, we might trap more energy than we want and get some climate change going on. Thermal imaging cameras, like I said, and night vision use infrared wavelengths, and then we use those to make pictures called thermographs, and that's what this is. This shows a thermograph of a home, and the red spots, this is false color, but red shows higher temperature. And so you can see all the windows in this house are leaking heat. There's not very much insulation there, and so we can see where a house would lose heat to the environment. Okay, and I did say communication. Remote controls are very common things that use infrared radiation to communicate. If you look at the end of a remote control, sometimes you'll see a little, looks like a clear plastic light bulb or glass light bulb, tiny little LED looking thing, and it really is an LED, except instead of emitting visible light, it's emitting infrared light, and then the detector on the TV or whatever that's a remote for will read that signal and use a computer circuit to do whatever it's supposed to do. Now, infrared is before red, so the next up is red light, and it's in the visible spectrum, which is light we can see. So 700, 750 to 380 nanometers. So these waves getting a little bit shorter, a little bit higher frequency, a little bit more energy. These are primarily important because our eyeballs can detect it, and so we can see because of visible light. Different colors are due to different wavelengths. White light is a combination of all of them, and if we take white light, we can break it up into different colors. In fact, you guys have seen that when you've seen a rainbow, if you've ever seen a prism. You'll notice white light comes in. This is a graphic from Wikipedia. Red light at the top, purple light or violet light down here at the bottom. Now, why is this happening? Well, when this light hits this surface, it refracts because it's moving from air into glass, which is going to change its speed. And then as it leaves the glass and enters the air, it refracts again because, again, its speed changes. And you can see that the red is not bent as much as the violet. So because it has a different wavelength, it bends a different amount. Violet light bends more, the red light bends less, and the other colors somewhere in between. So the different colors have different wavelengths, different frequencies. But you can remember their order. It's Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And that's the order of the colors because that's the order they go in wavelength from longest to shortest. Now, after violet, we have ultraviolet or above violet, UV. There's varieties of UV, and as you get further into the spectrum, they carry more energy. However, these are not ionizing radiation. What I mean by that is they don't strip electrons away from atoms. They can't really interfere with chemical bonds, but they can trigger chemical reactions. We can't see them, at least most people can't see them. Some people's eyes are a little more sensitive into the UV spectrum and see a little further in than is typical. Insects and birds, some of them can see into the UV spectrum. It helps UV kind of helps see pollen for insects a little bit more. So I think there's actually a shrimp that can see a lot further into the UV spectrum and sees more spectrum of the electromagnetic waves than anything else. Not sure why. But so UV spectrum, not so much for visual stuff, but it does carry energy. Not enough energy, like I said, to ionize, but enough energy to trigger chemical reactions, which is good, but also bad. Okay, suntan and sunburn are caused by UV radiation, but also vitamin D production caused by UV radiation. We get that energy, which helps the chemical reaction to produce vitamin D. Because it can carry enough energy to damage things, it is a good thing that most of it doesn't get to Earth. If it did, life would have a very much harder time here. Most of it is blocked by the ozone layer, and then we also do make our own artificial UV light to disinfect things, to kill things, or for fake bacon. Suntan tanning bed is using mercury vapor lamps to produce ultraviolet radiation to give you a suntan or cancer, whatever. Okay. Above ultraviolet, we have X-rays. These are shorter, again, 10 nanometers to 0.01 nanometers. This is ionizing radiation. Okay, this is the one where it's going to be fairly dangerous because it can start to break down and disrupt molecular bonds. However, it is very useful in the medical field because it can penetrate through relatively thick materials, which means we can see inside of stuff, which is handy. It's much better to take an X-ray to see what's wrong inside you than it is to cut you open to see what's wrong inside you. X-rays are not only used to make images, but they can be used as radiation therapy to treat cancers. So X-ray is a very useful ray. It was named X because when it was discovered, the guy who discovered it didn't know what it was. X was unknown, so this was an unknown ray discovered by accident when he actually saw an image on a ceramic plate when he was messing around with an X-ray source. And so these are actually very useful for lots of different things, from medical to figuring out the sizes and shapes of atomic crystals. We use X-rays for a lot. But there is another range, the gamma rays. So these are generally shorter than 0.01 nanometers, although there is some overlap and disagreement about how to classify X-rays and gamma rays. Gamma rays, one way to classify it is it's the radiation produced by nuclear decay or radioactive decay from the nucleus of an atom. X-rays are generally considered to be generated from electrons falling between energy levels. So not gonna get too much into that, but we're gonna consider the gamma rays to be the highest energy, shortest wave, highest frequency electromagnetic waves. And they are also pretty terrible. They have lots of energy. They can cause cancer. They can kill things. We use them in irradiation to sterilize different things. They can be used as a cancer treatment, but they can also cause cancer, so kind of caught in a loop there. And so these are used in the medical field. They are used to irradiate things. So we use everything from the very longest radio waves to the very shortest gamma rays, and depending on their properties, we use them for different things.